coordinate system, we need these three components, dl, a, and dv. Common challenge that we might often need to solve is that for any vector a, which is given in one specific coordinate system, which in this case it's going to be the cylindrical coordinate system, we have the projection along the AR, projection along the A phi, and we may want to describe this one in Cartesian coordinate system. And describing in terms of Cartesian coordinate system, what we are running after is just this AX and AY. And similarly, we can also be asked to see the projection of this into another coordinate system, which can be, this is a component. This is AR plus A theta plus A phi. Now, these A phi's, they are not the same. So this is cylindrical, okay? This is cylindrical, this is Cartesian, and this would be the spherical. And as a reminder, we may remember that for the Cartesian coordinate system, we have x, y, z. For the cylindrical coordinate system, we have r, phi, z. So this is common. And for the spherical coordinate system, we have r, theta, phi. Okay, just forget it. Okay. Dobry pattern. Привет. Okay, przepraszam. Okay, let's come back. So this is how we are going to work with it. And as a reminder, we said that in order to be able to identify what is AX and AY, we are going to use the similarity or the equivalence with what we are trying to do here. So let's assume we have a vector A, which can be described as projection of 3 units along the AX, 4 units along the AY, and 2 units along the AZ. We can make this a little better looking. And in order to find the angle theta, which would be between the z-axis and the vector A, we need to identify this. Okay, so we do the dot product between A and AZ. And that would be equal to 2. To find the angle gamma between the x-axis and A, this would be, we take the dot product of A with AX. Okay, so that's how we have to work this out. And as a result, here we're going to get the 3. Okay, we get this component here. This is equal to 3. And in order to find the respective angles, this will be equal to the magnitude of A times the magnitude of AZ. But we know that the magnitude of AZ is equal to 1, because this is the unit length vector along the Z coordinate system. Similarly, A theta is also, it's a vector which has unit length of 1. That's why we denote it with this beautiful head that we put it, this upside down triangle, something. So this is equal to 2 times the magnitude of AZ. So let's write this one times 1 times cosine theta. That's what we denoted here. And this would be equal to the magnitude of A times 1 times cosine. We denoted this one as gamma. So then, from this expression here, we can easily identify that the cosine theta is equal to 2 divided by the magnitude of vector A. Now the question is, for this vector A, what is the magnitude? We know that I think we can see this part. The magnitude of any vector A, this is denoted as the square root of 3 squared plus 4 squared plus 2 squared. And this is, and in principle, this is, I can also write this one, this is A dot A, so the inner product with itself, that's what it's all about, but we have this. And finally, we have 3 squared 9 plus 16, 25 plus 4, 29. So here we get the square root of 29. This is the cosine of angle theta, and here we find that the cosine gamma, this is equal to 3 divided by the square root of 29. Okay, so this is how we identify these angles. And now another question that we can come up with using these similar concepts is the following. Let's have a vector B, okay, a vector B, which can be equal to minus AX plus A plus 2AY plus 3AZ. Now, one question that we can ask is that what is the projection of A along the vector B? Okay, and how can we draw it? Vector A can be here, vector B can be here, and the projection is equal to, this is the projection. So this is A, this is B, the projection of A onto B is this. How can we identify this? The projection of A along the B, let's assume an angle phi, this would be, it should be equal to this, A times cosine phi, right? That's it. But now, how can we get, in a formal way, a magnitude which is going to be equal to A times cosine phi? This is going to be equal to, I have to read your comments, because sometimes in your comments you just tell to me, Professor, your microphone is muted. But no, we are good. So here we have A cosine phi. In this case, what would this be written in a formal way? This would be the dot product between A and a unit vector along the B. Okay. Now, this is not the best way possible, but this might be better. So A dot product with a unit vector along the B. Okay. So this is how we can find the projection of A along the B. And let's write the question. Find the projection of A along B. How do we do it? It's simple. We just need to identify this vector. And what is the unit vector U along the vector B? This should be equal to vector B divided by the magnitude of B. So here we have, what is the magnitude of B? Magnitude of vector B. This is how we denote it, and this is going to be equal to the square root of, what is this? -1 squared, which is the projection along the x-axis, plus 2 squared plus 3 squared, plus 2 squared plus 3 squared. So here we have 9 plus 1, 10 plus 4, 14, square root of 14. So this is the magnitude of vector B, and then a unit vector B along B is going to be equal to -1 over square root of 14 AX plus 2 over square root of 14 AY plus 3 over square root of 14 AZ. Okay. So, okay, that's good. Then now we know this unit vector, and then we can now answer this question. Find the projection of A along the B. In this case, the projection of A along the B, I need to find an eraser. Okay. Give me. So now, what is the projection of A along the B? Is that going to be, we can write this here, A is going to be A dot product with UB, and this is 3, 4, 2. Allow me to, we have the same A, right? Yeah. So let's write this. Okay, or no, 3, 4, 2 dot product with 1 over 14. 1 over the square root of 14 with a -1. The second component, it is 2 divided by the square root of 14 and 3 divided by the square root of 14. Then from here, we get that this is -3 over square root of 14 plus 8 over the square root of 14 plus 6 over the same square root that we use it a lot. And from this result, we can have the common denominator, which is square root of 14. 8 plus 6 is 14, minus 3, it's 11. So here we have 11 over square root of 14. So with this example, we also try to remind ourselves how we can identify the projection of any vector A along any direction. Good. Now this was a good exercise, but now let's go to our primary objective. Our primary objective was try to, once we are given the AR and the phi, we have to identify AX and the AY. Or similarly, we may have to identify what is the projection of AR, A theta, and A phi. Now, I can ask one question. How can you find AX? Okay, think about this question. You can raise your hand in the chat section, and you can provide your answer. I can wait for a couple of seconds. So to find the projection of A, which in this case it is described along the projection of AR and A phi, which is in the cylindrical coordinate system, we should simply write the following. So AX, the projection, is going to be equal to A dot product with AX. That's it. Okay. Or AY, this is can be written as A times AY. Okay. And in this case, the A itself, it is AR plus A phi dot product with AX. And now we write the same expression here, which is AR plus A phi times AY. Now, what this corresponds to is the following. So we have to identify, to figure out what we have in this case. And let's assume for a moment, let AR be equal to R cosine phi, okay? And let A phi be equal to 2 phi, okay? So these are just two projections, okay? And even without identifying these, we may have to draw the following. It should be, so let's assume we have this point, and this says along the AR, the unit vector along the AR is right here. This is AR, okay? And the unit vector along the A phi is perpendicular to this vector AR. This is the A phi. The angle between these here, it's 90 degrees. And if we are at some other point, something like here, we'd have the similar situation. So AR would be in the direction where the radius is increasing, so this would be the AR, and the A phi would be right here, okay? Now, why we draw this like this? Because even at this instant, we have to find out what is the angle between AR and AX. Now, let's try to identify here. AX, it's right here. This is AX. Let's draw this in red. And AY, it's right here. Okay, so it looks like if the angle here is equal to, let's say, what we denoted as phi. So this is the angle phi, this is phi. Because of symmetry, this is also an angle equal to phi. And then we try to solve this a little further. And And solve this a little further. This means that let's try to, we have here this term multiplied with AX. We get AR times AR dot AX plus A phi dot AX. Then we know that these two are unit vectors, and this dot product is going to be equal to AR times AX is equal to the cosine phi. This is the angle between these two unit vectors, right? So AR is right here, AX is here, so we get here cosine phi plus A phi dot AX. Let's have a look. A phi, it is extended this way, okay? And we have to, when we do the dot product with AX, let's blow it up in here. So A phi, it looks like it's something like this. AX, it's right here. And we are looking for the cosine of this angle. This angle, it is a wide angle. And the projection of the wide angle on the x-axis is a negative number, okay? It's this length. So the cosine of this wide angle is this length, but this length, it's so if this is an angle phi, the cosine of 90 plus phi, this is equal to sine phi. But do we have any positive or plus or minus sign? Any idea? So how can we relate the cosine 90 plus phi with what's the name? With the phi? Dikush mund ngre dorën tu? Angie? So we get the minus sign here, and this is minus A phi times sine phi. Okay, so this is how we can describe, or we can express this AX component starting from this and here and here. Now, similarly, we have to solve for this AY. In order to solve for AY, we just need to write that, we can rewrite this again. AY is going to be equal to AR, A phi dot AY, plus A phi dot AY. And here we have this is, what is A phi dot AY? A phi dot AY, the angle between these is just phi. So this is relatively easy. This is going to be AR cosine phi plus A phi dot AY. Wait a second. No, I have a mistake here. Wait a second. Sorry, this is a mistake. This was AR. Because the projection initially is described here, then this is, okay, fine. We should improve this. This is AR. So let's have a look. What is the angle between AR and the AY? The angle between AI and the AY, we can see this, it's right here. It is equal to an angle alpha. So we're talking about AR and AY. Between them, there is an angle alpha, which is equal to 90 minus phi. Okay, so it is this angle here. And this should be cosine alpha. So for these two angles, the inner product should be equal to cosine alpha. But if we describe it in terms of angle phi, this is going to be equal to sine phi. because we know that two complementary angles, like 30 and 60, the sine of 30 is equal to cosine of 60. So similarly, here, in this case, after a small correction, we have here AR times sine phi plus A phi. Now we have the angle between A phi and AY. A phi and Y, the angle is cosine. So here, this is equal cosine phi. So in this case, what we observe is that we have two equations, so let's cluster together what we wrote so far, and this is AY, okay, and the AX, it's here. Now, you've taken linear algebra, and it might be educating, or it might be a lead into our understanding, and also expressing several expressions using the, let's say, the intuition that the matrices provide. It's always good. So in this case, it looks like we can construct two components of a vector, such as AX and AY, and try to express these as a function of what we have here, AR and A phi, okay? So here we have a vector which is 2 by 1, here we have a matrix which is 2 by 2, and here we have another vector which is 2 by 1. In this case, the combination between AR and AX, it can be easily obtained from here, which is cosine phi minus sine phi, sine phi, and cosine phi. So you might have seen this matrix before because this is a purely rotational matrix, and so we can denote this one as a rotational matrix by an angle phi, and it is so we can use this one directly, or we can use the intuition provided from a previous course like this. And now this previous course, which is linear algebra. And now you can have a look, and we can try to have a look at this matrix here, which is 2 by 2, and we denote this matrix as matrix R. And let's try to find what is the determinant of this matrix R. The determinant of matrix R, it is a product of these two numbers minus the product of these two. And what we observe, we have cosine squared plus sine squared is equal to 1. So whenever the determinant is equal to 1, we are talking about a purely rotational matrix, matrix. Okay, so this was let's see. This was a derivation of how these components can be related with respect to each other, and we can try to. Wait a second. We can try to actually let's use these values. Let's assume for a moment. Do you have any question for what we did so far, or
no?
No, thanks. Okay. In fact, let's try to work this out. Let's assume that we have AR and A phi. There are these two values which are shown here, and we evaluate this AR and A phi. Assume, let's say assume R is equal to 2 and phi is equal to pi over 3. Okay. So if R is equal to 2 and phi is this value that we provide here, we can conclude that the AR, the projection of AR, it's equal to R is 2 cosine 60, because pi over 3, it is 180 degrees divided by 3, so we get 60. Cosine 60, what is cosine 60? So this is 30, this is 60. We know that the angle in front of the, the side in front of the angle 30 is equal to half the hypotenuse. So cosine 60 is 1 over 2. Sine 60, it is square root of 3 over 2. Okay? So in this case, this AR is equal to 2 times cosine 60, which is equal to 2 times 1 over 2. This is 1. And then the projection along the phi, it's equal to a phi, is equal to 2 phi. Phi, this is 2 times pi over 3. So this is simply 2 pi over 3. That's good. And now we have to substitute all of these values into the respective places. So this AR, this can be just 1. Imagine for a moment, this is 1. And the a phi is 2 pi over 3. This is 2 pi over 3. And let's assume, so if we try to draw this one, and let's do it, we should observe the following. So we have the radius, we selected it 2 at an angle of pi over 3. Pi over 3 is 60. 60 is right here. So this is the angle of 60. Radius is equal to 2, so I have 2 units. This would be 1. This would be 2, 1 and 2. And then we look like along the AR is right here. This is the direction of AR. We have a projection of unit 1. Okay, so this is 1. Let's add another one because we are at this point, but we have this vector. And along the a phi, we have 2 pi over 3. 2 pi over 3, if we want to project it how large it is, pi is approximately, it's 3.14. We divide 3.14 by 3, it's 1, times 2, it's a magnitude of approximately 2 units. So assuming we are trying to draw this one to scale, this is 1, 1, 1, 1, 1, and here we have got a quantity which is slightly larger than 2. Okay, so it's like here. So at this point in space, we have 1 unit along the AR and something more than 2 units. Who can divide this for me? This is 3.14 divided by 3, 1.04 times 2. This is equal to 2.08. 2.08. This is approximately 2.1. Okay, so let's do this the correct way. 1, 2. We had also 10%. We got right here. So these are the 2 projections. Okay, this is an angle 90 degree, and it means that at this point in space, the vector itself is this one. Okay, so apparently, given these values, this is the vector A. Okay, at this specific point in space. Now the next question was trying to identify what was the AX and the AY. So if we use this expression here, which we have written, we can say that AX is equal to, we multiply the first row with this column, and what we obtain is that this is equal to cosine phi, and cosine phi, it was 1 over 2, right? This is 1 over 2 minus square root of 3 over 2 times 2 pi over 3 times 2 pi over 3. This is AX. AY is equal to, we multiply the second row with this column. We get here sine phi is equal to square root of 3 over 2 plus cosine phi is 1 over 2 times 2 pi over 3. Okay, here this is a vector which is 2 by 1, 2 rows, 1 column, and this, if we calculate the numbers precisely, we get here, we cancel this out. This pi cancels the 3, we have here 0.5 minus 1.7, approximately 0.5 minus square root of 3. So this is minus 1 over 2, minus 1 over 2. This is AX. AY is equal to, let's cancel this out, pi divided by 3. They almost cancel each other out. So here we get square root of 3 is 1.7. Divided by 2 is 0.85. So here we have 0.85 plus 1. This is 1.85. Good. 1.85. This is more or less the projection along the AY. So it looks like how much would this project onto the x-axis? Let's try to do the best thing we can, which would be, let's try to draw the vertical line. This is what the vector is, and this is here. It looks like along the x, we have something which is approximately minus 1.2. It looks like right, okay? Because the projection of this vector A, which we can draw this one in a double red line, it is projected along the x-axis like this, okay? If we try to do it to scale, it's really something, it is a negative value because it's pointing along the negative x-axis. So this is approximately minus 1.2. And the projection along the y-axis, it is, so we have to consider, this is the projection along the y-axis. Maybe we can draw it like this. So this length, approximately, this is this much. And this much, it is slightly less than 2. So we did not do an AutoCAD drawing here for sure, but using this piece of paper, I tried to do the best I could. So it looks like this projection on the y, it is slightly shorter than this 2, which is shows at 1.85. That's good. So we kind of confirm, to the best of our drawing abilities, that we converted in a good way the vector A, given in cylindrical coordinate system, we projected it down to the Cartesian coordinate system. Now, okay, so now in the, let me see, because we can solve a similar example also in the spherical coordinate systems, because this was Cartesian and cylindrical. But before we go for that, I would like to give a short break